Do you know which individual components actually wear inside a shock or strut? If you aren't sure or can't answer this question easily, then you're probably having difficulty diagnosing shocks and struts and will definitely be challenged when it comes to talking to your customers about wear and ride control performance. Hi, I'm Mac, and I'd like to show you a few things about shock design that will help you fill in the blanks about what you may already know and make it easier to talk to your customers about shock wear. When I ask a group of technicians what they think wears out first regarding shocks and struts, the most common answers are the obvious ones. The effects that you can see, like oil leaking from the upper seal or mounting bushings that are damaged or loose. That's good, but those things are visible and definitely not the only things. The things that you can't see are what I want to point out to you. For example, on today's vehicles, if the shock upper seal becomes worn, what's the first thing that will leak? Will the oil leak first, or will the pressurized nitrogen gas leak out more quickly? Can you see evidence of the leaked gas, or is that invisible to you? And if the gas does leak, what happens to the shock's performance? You see, just understanding that this condition can occur makes it easier to explain and justify replacing shocks and struts after 50,000 miles. To understand more about wear, let's take a look inside a typical twin-tube shock. This is a cutaway drawing that shows the cylinder, piston and rod assembly, and the base valve. We all know that movement and friction causes wear, so there's a couple of obvious potential wear points. One is at the top seals where the piston rod rubs as it travels up and down. The result is either a fluid or pressurized gas leak. The same piston and rod travel causes wear on the cylinder walls and piston seals. This wear can cause a fluid bypass along with a drop in performance. But these are just a couple of the wear points and actually not the most common cause of poor ride control conditions. Here are some illustrations of ride control conditions: tire cupping, nosedive, body roll, ride harshness, and so on. What specific components in a shock or strut are designed to control these conditions? If you know the answer to that, then it's easy to understand what wears and why or when you would want to recommend replacement units. Inside of the piston and base valve assemblies, there are a variety of fluid passages and individual valves. The reason for the variety is to provide different damping forces for each driving condition. Big bumps, little bumps, no bumps, high speed, low speed, and so on. Let's look at a simple illustration of a multi-stage valve. In this example, there are 3 different stages. The third stage might be for large vehicle movements or big bumps. The second stage would be for medium ones, and the first stage for light bumps. Each valve is actually a calibrated metal disc that covers a fluid passage. When enough forced fluid, created by piston rod movement, pushes against the disc, it flexes and lets fluid through. The flexing movement of the metal disc eventually causes fatigue, and the result is performance loss. As you can imagine, a third stage valve may not open and close very much per mile driven, because most of us aren't driving over that many big bumps. The second stage might open more frequently, and the first stage valve is probably moving all the time as we drive. How much movement are we talking about? Well, a piston and rod assembly can have as many as 1,500 to 1,900 movements per mile driven. During 50,000 miles, that can be over 75 million times. And that means the first stage valve disc is flexing over 37 million times in that same 50,000 miles. As with any piece of flexing metal, it will experience fatigue and eventually failure. So let's think about all this. First of all, when your technicians perform a bounce and jounce test, which means pushing up and down on a corner of a vehicle to see how much it bounces, which stage valve wear are you actually checking? And now that you understand how the stages work, do you still believe this is an accurate or fair test? Well, it probably won't give you a complete assessment of wear, will it? And then let's consider what happens to the tires. As the first valve wears and the shock or strut allows more movement, What happens to tire performance? Can you see that this wear is what causes ride harshness? If the tire performance is affected, what happens during braking and cornering? How well can the vehicle handle unsmooth or slippery road surfaces? With these illustrations in your mind's eye, I hope that you better understand shock and strut wear and why industry experts suggest replacing shocks and struts after 50,000 miles. For more information about using the correct language for a 50,000 mile recommendation, be sure to watch the KYB TV video entitled Why 50,000 Miles?